again. Good morning, everybody. And we heard a lot about SK, so I should try to make it a bit quick. We also heard a lot about galaxy clusters, so I will not get into too much of a discussion about that. Right, so I'll be talking about extragalactic surveys with the SK. So here we can see all those dishes that Yogesh talked about just now. We had SK mid and SK low. Right, so we also saw this. It's a collaboration, international collaboration. So I will just highlight some points because he has already given you a brief information about the project. But 40% of world's population is involved into a SK project. So that is quite interesting. So it is indeed a mega project. And that means also that students at one point or the other, they will be using SK. And so it's interesting to know what this instrument is, even if you don't work in radio astronomy. So that's something which I wanted to show here. Then over here, you see the construction phase. So of course, the idea came up in 1991, and then the telescope design was started in 2008. And then this SKO was built in 2011, and the site selection was done in 2012. So all this we heard a lot in detail. What I would like to highlight in this particular slide is this part. In 2013, people were asked to submit proposals for SK. And with this proposal, when it went to the SK head office, people looked into the science case, the requirements that they want to establish the science case. And based upon that, this cost ceiling was estimated. So that's why people had submitted these proposals in 2013. And of course, from India also, there were proposals submitted from NCRA, led by Preeti, Ruta, Dharam, Yogesh, and everybody. So there were at least 3 proposals submitted from Indian side. From the French side, I had submitted also a proposal at that point. Right. So with all that information, then the preliminary design review committee was made because of all sorts of requirements that people had for their science that they wanted to do with SK. And then this prototype instrument started to come up in 2016. And then we have been seeing all sorts of interesting results which has come up with those kind of prototype instruments like the Meerkat and Australian SK Pathfinders. They have shown excellent results that we saw even from the talk of Amitesh this morning. Right. So since 2023 onwards, they are going to now work on the design of SK2. That's what was said. But I think we are still not done with SK1 phase construction. I think that's what is going to be in the next couple of years. And this is why from now until 2028, it's going to be a very interesting period for this project and all sorts of science case that we want to build, because the SK phase 1 will be ready by 2029 and it will be available for the users community. Before that, there will be a lot of data commissioning phase and all sorts of tests. That's what Yogesh talked about. So there will be also jobs for students in commissioning. So if you do look at data and if you are interested in commissioning of the data, which is what I've been doing since all time long in my career, I think you will have possibilities of postdocs. So one has to remember that in the next 5 years, this is where you are heading towards. Right. Now, this is SKLO, which is in Australia. We heard a lot about it already in detail from Yogesh. That was great. What is interesting over here is this is similar to LOFAR. So SK at LOFAR at 50 megahertz shows 20 arcsecond resolution image at 7 millijansky per beam sensitivity. But SKLO shows better resolution images and very high sensitive images. The noise is 26 microjansky, so it is 25 times better in resolution and 8 times better in sensitivity compared to LOFAR. So whatever great results that we have been seeing until now with LOFAR, SK is going to do far better than that. So we are going to have lots of discoveries, lots of those kind of ordering structures that we saw. Many new things will come up, diffuse emission in galaxy clusters, all sorts of things that we will be discovering. So radio astronomy is entering into a very golden era, as people say, and it's true. It is going to happen. So be excited about this project and don't give up. Right. Now we go towards SK-EMIT. SK-EMIT is again a very interesting instrument because it actually opens radio astronomers to do cosmology and to do really radio observations or radio studies at higher redshifts. We were always limited with redshifts. We were not really going far, but SK-EMIT, thanks to all sorts of H1 as well as extragalactic spectral line data that it will provide up to the frequency of 15.4 gigahertz, we will be able to actually finally catch up with optical astronomers and infrared astronomers, which was always a bit of a challenge for radio guys. This is why it is really interesting to now build up projects with optical and infrared people, and this is why I'm here. Okay, so actually, in comparison to GMRT at 1.4 gigahertz, it has 2 arcsecond resolution and 30 microjansky noise per beam for 1 hour of observation, and SKA mid at 1.4 gigahertz give you far better resolution and really 2 microjansky level noise. So it is 5 times better in resolution and 50 times better in sensitivity compared to the GMRT. And here is the comparison given for the JVLA. So it is a very important instrument, SKA mid, and so is SKA low. So we also saw this, the flow of actually the data, which happens with the SKA Regional Steering Committee. And I'm a part of this at some level. I'm also working with them. This is why I know a bit about the projects that we people are proposing to do with the SKA. Right. Now, what is interesting is all this is about SKA. We heard a lot. Now we have to see what we have in hand for the moment. And we have got the SKA Pathfinders and precursors. We have got LOFAR, which operates between 10 to 240 megahertz, which is the kind of science we have been doing with LOFAR. We can do easily with SKA low at better resolution and better sensitivity. So, of course, there's a lot of discovery that is expected. We have MWA, which goes up to 300 megahertz, again overlapping with SKA low, but here we have high sensitivity and better resolution than MWA. GMRT stands out to be very interesting because it overlaps not only with the low, SKA low, but also with SKA mid. So it has an important place again, and it has played an important role for the LOFAR commissioning. It will play an important role for the SKA commissioning. So everyone should know a bit how to reduce GMRT data if you want to use SKA in the future. It will always help you. Right. Now you have Australian ASKP, which is at 700 to 1800 megahertz. It's doing good. We've already seen the results from Amitesh talk, and it is going to have overlap with SKA mid, whereas Meerkat, actually, it's 10% of SKA mid. And so Meerkat is already showing wonderful results. Right. So that's what I wanted to show here. Now, if we compare the sensitivity at different frequencies, what you can see, this is MWA, this is LOFAR, a very narrow band. GMRT presses out a large band of frequencies. So it goes towards SKA low as well as SKA mid. So GMRT stands out to be important when you want to calibrate the data at those particular frequencies. One needs GMRT for calibration of SKA data as well. We also have JVLA over here, and these are the sensitivity of SKA phase 1, and this is the sensitivity for SKA phase 2, which is going to be afterwards. So we have all this experience is going to be important, and it will feed into all sorts of science that we want to do with SKA. So if you have science projects going on right now, I think it has better chances to continue if you have great results also with SKA once it is commissioned. Right. Over here, what I show you in this particular table is the resolution. So your SKA low goes from 11 arc seconds, and then when you go higher up to SKA mid, the resolution of the instrument goes up to 0.04 arc seconds. So at that particular resolution, why is it interesting? It's because you can start to really resolve out point sources, really distant sources, which were never resolved, where they were very faint. And now we can start to actually have resolutions similar to optical infrared telescopes, which was not possible before. And at lower resolution, it is around 11 arc second, which is also good because you will start to detect lots of diffused faint emission, like in galaxy clusters, like those ordering structures, which was not possible because of noise before. Now we will be able to detect it more and more with the SKA. So this is why it's interesting, this particular table for comparison. Over here, we can see the timeline, the multi-wavelength synergies with SKA. So it's not a very beautiful plot, but so what we can see is this is when the SKA is available for observation in 2029 for once the commissioning phase is over, which is going to be in the next couple of years. Once this is done, you have all sorts of instruments which are available to do synergy science, with SKA. So you have SKA here, but you have CTA, you have HESS, you have MAGIC, Athena, LSST, JWST, MSC, foremost, Euclid, insist, everything is viable actually. So if you start to master this particular, if you start to get into the commissioning of SKA, you can start to do all sorts of synergy science with these telescopes. So having overlapping projects at radio, optical, infrared wavelengths is a must today if you want to really do great science, because there's a lot of science to do, a lot of discovery to do. So you can also see here the resolution I have just put. SK low resolution is between 11 to 4 arcseconds, as I showed you earlier. SK mid is 0.7 to 0.04. We have Athena, where we can, NCTA, we can compare the images at SK low to detect the diffuse hot emission from the intracluster medium, for example. And at very high frequencies at SK mid, we have all sorts of instruments here with matching all kind of resolutions. And then we can do science because we can resolve those faint galaxies, star-forming galaxies. So this is why this is interesting. Now, these are the different working groups that have been identified for the SK project. So extragalactic, cosmic magnetism, cosmology, EOR, extragalactic spectral lines, H1 galaxies, our galaxies. So this was all extragalactic, and these are the galactic projects with the VLBI, gravitational waves, and high energy cosmic particles. So there are lots of science working groups. So if you're interested, just contact the chairs and you can be a part of that working group. There is no big deal, you don't have to follow any more procedure than that. You have to just write to the chair, express your interest and join the working group. It goes like that. So my interest is actually to study the H1 gas in nearby galaxies. And Sudhanshu showed a very nice image of Cartwheel galaxy. It's a spiral galaxy. So here we show a simulation of H1 emission from a typical spiral galaxy, where you see all those kind of streams of bright H1 emission, with more dense H1 emission coming from the central region, and all sorts of diffuse H1 emission as well. So it is interesting to overlay and to see at optical also if there is any kind of correlation between those spokes that we saw in his images from optical, and if it overlaps with these bright streams of H1 filaments that we see in these spiral galaxies. So that's one of the interesting work. This is simulation, but this is real data, and it shows similar results. So how do galaxies interact with the surrounding cosmic web, and what is the feeding and the feedback mechanism which is going on? And SK is actually going to probe really H1 column densities up to 10 to the power 18 per centimeter square. So it's really going to go very deep. Very high sensitivity images will be produced, and we will detect all sorts of those diffuse H1 maps, which was not possible before So, but some work is already going on with all sorts of those instruments, the Pathfinders or precursors. So this is one of the image which comes from Meerkat. And in Meerkat, what you can see in this image, this is a galaxy cluster. At the center of the cluster, we have a bright galaxy cluster, and this bright galaxy in the cluster is having some disk emission from H1 emission from the disk region, but we also see, which is around 10 parsec. So you see all sorts of H1 structures in the galaxy clusters from 10 parsec to tens of kiloparsec scale. You can see long filaments. You can see just a compact emission from the central region. What it shows is when you start to go towards the center of the cluster, the galaxies, they start to lose the gas due to pressure stripping. And so you will have less and less H1 gas in the center of the cluster, but you will detect more H1 in the outskirts. So this is coming from Meerkat, and this is an image from Vallabhai. Again, it's the same thing. This is a galaxy cluster, Hydra cluster. When you go towards the center, you have less prominent H1 emission or more compact, but when you are at the outskirts, you can see lots of the galaxies are loaded with H1 gas in these regions. Right. So it is also interesting to detect if there are more and more such filaments, and if there is any kind of correlation between the spokes that we saw in the Cartwheel galaxy and in the filaments that we see in this kind of galaxy clusters, and are there more and more H1 gas in the filaments and less in the center of the cluster? That's something else that we want to see, really how gas interacts with the intra-cluster medium. Right. So that was about H1, but we can also do all sorts of study of star-forming galaxies, which are very faint, which were not really detected very efficiently in the past with radio imaging observations, and which will be possible with SKA. So what I show you over here is optical observations with MUSE on one of the galaxy clusters. We detect lots of galaxies in the Muse data because of its thanks to its sensitivity. And what we see is the foreground and the background galaxies in the cluster. So not lying in the cluster, but they're either in the foreground or background. They tend to show all sorts of emission lines, as you can see in the spectra here. But when from the agents of these galaxies, but when you go inside the cluster, the galaxies which are lying inside the cluster, there as they are depleted of their gas, they don't show any emission lines. So they show absorption lines. And these are actually red giants and they are poor in gas. So that's what we see here. But again, there are certain galaxies which do show some emission line. And those are those star-forming galaxies that we are interested in. So these were the cluster members, and among the cluster members, most of the spectra was like this. So there was no emission line, but few of them they showed, which included also the central galaxy, which was having some gas. So we computed the star formation rate with the optical data. And what we see is when you go away from the center, you will have more and more star formation activity. But inside the center of the cluster, you have very less star formation because the galaxies, when they fall in the center of the cluster, they tend to lose their gas. So that's what we see here. So star formation is quenched due to ground pressure stripping in the center of the cluster. But these
same thing with respect to H1 mass.
With the H1 mass, we have not got so much of data, but we have done some work, but it's at really very low redshift, so that is 0.2. We couldn't go above that. We don't have a lot of points, but we do see some trend increase in the H1 column density when we are going slightly higher. But as I say, we don't have enough data to build a proper statistics, but we want to do that with SKA. That's one of my projects. Right. So we come here, and what I show you is pre-2010, when I was a student. At that point, the sensitivity of those instruments were really not great. I mean, we could go up to the faint galaxies that we could detect was up to 0.01 millijansky. In pre-SKA phase, so this is where we have low far upgraded GMRT, we can go up to 0.01 millijansky, but when SKA will be operational and we will have the high quality data, we will really detect galaxies of microjansky level. And these are the star forming galaxies. Is there? William is there?
No, I don't know that.
Yeah, so if he's not there, then I'll continue. Okay, please check if he's there. Yeah. So that's what we will detect, these new class of sources. So new population of star-forming galaxies and AGNs will be detected, which are the faint population with the SKA. I don't know if I should get into this because I don't have much time, but what I want to show you, it's not just about H1. There are also other extragalactic lines which will be detected with the SKA in the SKA midband. And those lines are those redshifted lines like the CEO, the CS, and TN. All these optical astronomers, they are very well versed with this kind of lines. And we will detect them with SKA in the SKA midband. So this is interesting also. Then we will start to actually talk with optical astronomers and about all sorts of emission lines that we see, all kind of cooling flows which are happening, and we'll start to detect CO, molecular clouds in galaxies and clusters. Right. So again, I will not get into this because it was already explained this morning by Surajit, and also a bit Alexander covered it, but this is a typical galaxy cluster. What you see over here is the cosmic web, and inside the cosmic web you have dense regions which are called as the nodes, and the nodes are fed by filaments, all the galaxy and gas, so they grow bigger and bigger. And they create voids. So you have voids, you have filaments. The filaments are feeding galaxies and gas in the nodal area. And this is where the cluster is formed. This is why cluster is the most dense region in the cosmic web. And then you look at the galaxy cluster, it is actually a combination of different galaxy groups, which are all into merger. You have the dark matter mass, which is dominating 80% of the mass of the cluster, and you have 15% of diffuse hot gas in the intracluster medium, and 5% of the baryonic matter, which is coming from the galaxy groups which are under merger. So it's a combination of many things. So actually, it's very interesting to study galaxy clusters because you get to not only study the intracluster medium in X-rays and radio, but you also get to study the independent galaxies which are interacting and falling inside the cluster. And that you can do with infrared, with optical. So you can do all sorts of science with galaxy clusters. So looking at the X-ray data, we can classify galaxy clusters into cool core and merging. Merging clusters is what we saw this morning, where you will have big, large structures which are not circular. You will have shock regions, etc. And cool core is where all the activity of merger has almost stopped, terminated. it, and the cluster is cooling down. So it's really a compact image. So these are extended, these are compact if you look at the image in X-rays. And these ones, these merging clusters, when you look at them in radio, they show this halo that we saw, raylings, the shock regions, and ultra-steep spectrum radio halos. And when you look at the cool core clusters, they are the ones who host mini halos. So the presence of radio emission is interesting. Why do we see this radio emission? What is the impact of this component on the thermal intracluster medium, and the correlation between cluster dynamics when it is cool core, when it is merging? Is it changing, or how can you correlate that with the presence of radio emission? Right. So we also carried out survey over several years. We have been detecting also all sorts of radio halo, mini halo, and ultra-steep spectrum radio halo. So I will not get into that. What I want to show you over here is the simulation which was done, and where people showed that galaxy clusters host radio halos, and we expect at least hundreds of halo emission at every redshift in the SK low band and in the SK mid band. However, we are at this stage. We have detected almost 400 clusters hosting diffuse halo emission. So this is what we did, but there are others also. But we have, in total, there are 400, but at each redshift, we are supposed to be detecting hundreds of halos and radius, okay? So we don't see that yet. So there is a kind of a gap, a discrepancy which is there. And this discrepancy have to be filled. And the population which is missing here is this population of ultra-steep spectrum radio halos, which are only detected at very low frequencies. And LOFAR has been playing an important role in detecting these populations. And in future, SK is really going to fill this. As you can see, with SK, we are expecting thousands of them at each redshift and not just 100. So because of the change of sensitivity, same is the case with SK mid. Also, depending upon whether it's a cool core or a merging cluster, you will either see a mini halo or halo, as I told you. But at the same time, it's possible that you will have a cool core cluster hosting a giant halo and a halo. So it's not always very hard and fast division, but sometimes you will have special cases or outliners where your cool core or emerging cluster may not host a halo or may host a giant halo. So there is this mix-up which depends upon the dynamical state of the cluster. So it's very important to study the dynamical state of the cluster and then correlate these emissions. Right. Then we can also see that when the cluster starts to cool off and there is no more merger activity happening, then the cold gas starts to dominate in. And this cold gas is rich in molecular gas and it emits CO emission. And so then when we did observations with IRAM, we could detect CO from the center of those cool core clusters. Not many were having cool core CO line detected, but some did. And so we can do this kind of work with SK. So this is our sample. We detected only in the ones which are marked in red. CO upper limits are marked in blue, and in red we had some sort of detections. So that's what I should show you. Right. So we are now having this collaboration going on with IISc and IIA, where we will be going on working on these projects that I just showed you. And this project is called High CLOGS. So if someone doesn't know what CLOGS means, actually CLOGS means cluster and galaxies. So gas emission in clusters and galaxies, something like that. I forgot now the full form, but CLOGS actually means those Dutch gardening shoes. So it looks funny, but that's what it is. So the goal of our proposal is actually to do radio and multi-wavelength study of galaxy clusters and to study gas interaction in galaxies and within the groups and within the clusters. So this project is in collaboration with Alexander. We heard him this morning. He's a very good theoretician. We have Nirupam, who is an expert in H1. So we have him. We have Muthu, who is an expert in optical spectroscopy. So we expect him to help us a lot with all our optical observations. We have also Subhashish from NCRA in our project, but it's open for collaboration. If you are interested, please come and they will be happy to collaborate. We also have two research fellows who have been hired on our project. So there is the JRF, Saiva, she's working with Nirupam, and we have the SRF who has got hired today, if he doesn't know. So he gave a talk this morning, Pratik Gupta, and so he will be working with us. So funding is also, we have some extra funding available. So if any student is interested, please approach us. We can see what project we can do. Right. So SK has been also organizing all sorts of data challenge. Data challenge 1 was where they showed that all those
Wrap up in
2 minutes, yes. So they will they will be detecting new population of star-forming galaxies and AGNs, which were faint and not detected in the past. In SK Data Challenge 2, they did simulation of the H1 data cube, and then people detected all sorts of H1 emission. I have participated in the challenge, but also in building the mock data. And then this is the data center. So to analyze this kind of huge data set, we need really high computing facilities. So the country should be well equipped with that. If we have that, only then we will advance in analyzing this or reducing this data. Otherwise, we'll have to depend on someone to help us. And so I think India doesn't have this cluster, but I think Yogesh has said that it is coming up very soon and it will be available. Finally, I just wanted to show you this. So the people have submitted their proposals for SK users case. As I said, in 2013, it was asked, people were asked again to submit or modify their existing proposal based upon the specifications which are now available for SK. And there are like 62 proposals in all submitted from all over the world. From French side, there are 8%, and from the Indian side, there are 6% proposals among all of them. 6 from France, 3 I'm leading on extragalactic users case, so exactly related to my topic, and 3 are planetary scientists. And from the Indian side, we have 4 proposals, and 1 is from Uday Shankar, and 3 are from NCRA, Ruta, and Preeti are in Beirut. So my science case is origin and evolution of non-thermal radio emitting plasma in galaxy cluster, dark and baryonic matter interaction in lensing clusters, cluster environment and gas interaction, and 21 centimeter observation and imaging. So that's it. And finally, this is our SK France roadmap. So the idea, the coordination came up in 2016 because we don't have so many active radio astronomers in extragalactic, or anyway, the radio astronomy community was always a bit small in France. But slowly the interest has been building up with time. Then there was this SK book which was written, and with that book, people got more and more involved with the SK science. And finally, it has been growing, and it has become an official member. So it was shown that they are trying, but no, now France is an official member of SK. The agreement has been signed by the country, and so you can see since 2022, now it's an official member. So we have all sorts of community which is growing from 2.2% to 8%. The growth has happened from 14 to 2019, and they are participating in all sorts of challenge. And SK Data Challenge 2 was won by by the French group. And that's where I stop. That's the summary. But there is huge possibility of synergy projects. There is a lot of interesting work that can be done with optical infrared astronomers and even with theoreticians, of course. So if you are interested, please contact. I'm very happy to collaborate. Thank you very much.
in time for maybe a couple of quick questions. If there is any here or online, can one of you have a question?
In galaxy clusters, which are being observed. So are they observed as a radio halos or?
No, in them, halos have been already detected and confirmed. So I think it's 400 or more than 400, but up to some number like that.
Okay. Recently, I collected all data. So it's around 230 galaxy clusters which are showing radio halo emission.
Yes.
But there are others which are showing radio Rayleigh clusters. So I was thinking that 400 is for it's the combined.
Yes, it is combined. Yes, I think I'm putting combined. Yes. Yes.
Is there any question in the online?
No. Okay.
Then let's thank Mamta and we
Long live India and France friendship.